Before we discuss simple microscope, compound microscope and telescope, it is important to know about this concept of angular size of object. Angular size of object is a pretty easy thing. When you look at any object, suppose you are looking at a tall object and this is your eye. You are looking at an object, then if you want to see the lowermost point, you will look in this direction, and if you want to see the uppermost point, you see in this direction, and this angle subtended at your eye is what we call as angular size of the object. This was there in units and measurements in class 11. Now this gives you some interesting fact. What is that? Okay, so this is a straight line from your eye. Oh my god, there are two straight lines. Okay, now if you keep an object here, say there is an object, I want pen, where is my pen? See, that line gone. So there is, if you keep an object here, say if you keep an object here, then this will create an angle, say theta 1. Now the same object, same size, you keep it away, then that will create a smaller angle called theta 2. So theta 1 is greater than theta 2, but object size is same. This is why objects appear smaller as you go away from your eye. For example, this remote, when it is close to my eye, makes a larger angle in my eye, but when it goes away, it becomes smaller in size. The angle becomes smaller. The object size does not change, but the angle created decreases. That is why distant object appears to be smaller, the nearby objects appear larger. This is why, see, these pen and the remote are all of the actually not the same, okay, approximately same size, but by keeping one pen near my eye and the other one away from this one, I am creating different angles. Now this pen creates a larger angle and the other creates a smaller angle. That is what I am indicating in this diagram. Okay. Now if you want to see an object larger in size, if you want to see the details, how to look at it? It should create a larger angle. If you want to see the details, it should create a larger angle. So object should be as close to the eye as possible. So if I keep it very close to my eye, it creates a very big angle. But problem is that the image is blurred. So where should I keep this to see it in the largest size but full detail? That is at least distance of distinct vision. So if I keep it at 25 centimeter, I can see that in the largest size. But this creates strain here. If you look at the object like this, long time, it pains here. Okay. So this is related to the concept of angular size. I was telling that to see an object clearly and in the largest size, so clearly and its largest size, it must be at a distance of d from the eye as shown in the diagram. So whatever your d is, you keep it there. So the object is here, this distance is d, and we assume that angles are very small. That is why we say tan theta of the object theta O equal to h by d, or even theta equal to h by d. This is called angular size of the object when it is kept at d. This is the largest angle an object can create, largest angular size. Fine. Now see this diagram. An object of height h is kept at d 25 centimeter and creates an angle theta. What will happen if you bring it closer? The angle increases, its size appears larger, but will it be seen clearly? It will not, because within this distance the images are not clear. So if I have at d, I will see it clearly and largest, but if I bring it between eye and the least distance of distinct vision, it is seen in largest size but not clear. That is shown in this diagram. Now we will discuss the purpose of a simple microscope. What is the use of a simple microscope? A simple microscope will help you to do something normally that you can't do. I told you before, if you want to see anything largest in size, in its largest size, it must be at a distance d from the eye. If you keep it within this distance, I said you will be seeing that in larger size, but not clearly. But a simple microscope, which is a convex lens of short focal length, will help you place an object within this distance and see that clearly. Simple microscope will help you to see, help you to place an object within the least distance, but I told you within least distance it is not clear. No problem. This lens will create an image beyond D which you can see. What is the advantage? This image may have a larger angle than the object, and that can be seen from the diagram. I will show you, that is very clear. I tell you, see, if this object were placed here at D, suppose you keep it here same height, then this would have created a smaller angle. See, this is theta of the object, but this lens will create an image on this side, and that is seen at this angle theta. Let me call it as theta of the image, and we can see theta of the image is greater than theta of the object. So what will happen? The small object here will appear as a large object, magnified. That is why simple microscope is also called magnifying glass. It is also called magnifying glass. What is simple microscope? It is a magnifying glass. It should be a converging lens. It must be a converging lens. And what about its focal length? Of short focal length. Converging lens of, so simple microscope is also called magnifying glass. It is a converging lens with a very short focal length. I will tell you why it is a very short focal length little later when we start the discussion. Okay. It helps you to place object within D and gets their images enlarged and see them in a larger angle, so that appear larger. Okay. Now what is the detail of all this? What is simple microscope? A simple microscope is a converging lens of short focal length. I told you, object is placed either, okay, that is another point. Where is the image formed? In optical instruments like simple microscope and telescope, compound microscope also, microscope and telescope in generally, we use a term called angular magnification, which is a ratio of angular size of the image by angular size of the object. Okay. This is generally written as theta I by theta O. So magnifying power m is equal to theta I by theta O. If this is greater than 1, we will say it is a magnified image. It is called a magnified image. So what is angular magnification? It is a ratio of angular size of the image by angular size of the object. It is given by theta I by theta O. But one condition, that these two angles must be compared only when the object and the image are at the same distance, because we know when distance changes the angle will change. So here we have to keep either at D or at infinity. Image must be at D, object must be at D, then we will compare whose angle is greater. Otherwise you keep image at infinity, object also at infinity, then you compare their angle, then whichever has got more angle, that will be larger. So we normally need a image angle larger than the object angle. For example, suppose that this is I and this is the least distance. Suppose the object has a size h here, making an angle theta O, and at the same point suppose you can create an image which is larger with h dash, which will create an angle theta I, then theta I by theta O is called the magnification produced in that one. So this is very important to understand, angular magnification, and there is no unit for that one because it is angle by angle, is a dimensionless quantity. In a simple microscope there are two possibilities. Okay. Before that, in a simple microscope you have this eye, and we will assume that the lens is very close to the eye. Lens is very close to the eye. This distance is neglected, and we also assume that lens is a very thin lens. These are practically not possible. Okay. So this is the principal axis of the lens. Now this is the focal point. This is the focal point. You can place an object either at the focus point or within the focal point. So what is the position of object in a simple microscope? Position of object in a simple microscope is either at the focus, that means here, or within the focal length, or somewhere here. These are the two possibilities, either at the focus or within the focal. This is the focal length. These are the two possibilities. Fine. What is the difference? What is the difference in the final image? The difference in the final image is this. Difference in the final image is, this is the principal line. Suppose this is the focal point. Now you place an object here. If you place an object here at the focus, where is a final image formed, that you can find out using a ray diagram. One ray will go like this, another will go through the optical center. This ray will go through the focal point on the other side, and the image will be created here at infinity. So if object at F, image at infinity, you know this. When the eye will not see the object, I will not see the object, I will see the image at infinity. When the image is at infinity, the vision is relaxed. We call it as relaxed vision. So simple microscope has a relaxed vision mode where the object is at the focal point and image is at infinity. That is the first thing. Second one, simple microscope. This is the observer's eye, this is the lens, this is the focal point. If the object is within the focal length here, what will happen? You studied this, the light ray will go like this, one will go like this, another will diverge a bit, and you will get an image somewhere here. That is the image. Fine. If you want to see this image in the largest size, where should it form? If you want to see this in the largest size, this should form at D. So when you have an object placed like this, with you are watching through a lens, you will not see the object, but you will see the image which is at D. So the final, okay, there are other positions also at F and somewhere here you got. So you can move the object from the focal length to these points. You can vary that, so the image will also move from infinity to D. So image can be anywhere between D and infinity depending on the position of the object, but we are interested only in the two extreme cases. One, the final image at infinity for relaxed vision, and the final image at D, okay, final image at D. For what? For largest size. To see that in the largest size, we take this one. But the problem is that this is not relaxed. This gives you strained vision. In our syllabus, we will take up only on these two extreme cases, and we will derive equation for magnification in this case and magnification in this case. We call it as magnification at D. This is called magnification at infinity. That is what we are going to do next. Derivation of these two magnifying powers. Before we start the derivation, you should understand that the angular size of an object in the largest size is calculated using this diagram. Keep this in mind. So during the derivation, this is the first step. When the object is kept at the least distance of distinct vision D, then the angular size is given by h by d, where h is the height of the object, d is the least distance of distinct vision. This is the angular size of the object. Now let us take a simple microscope with the final image at D. Final image is at D, and for this we know the object is kept between focal point and the optical center at a distance u. We adjust the position of the object such that the final image is seen in the largest size. When it is seen in the largest size, this distance equal to least distance of distinct vision. What we want is the magnification. And what is the definition of our magnification? Our magnification is defined as magnification when the final image is at D is defined as theta of the image by theta of the object. Out of this theta of the object, when the object is kept at D, it will create an angle h by d. We studied this previously. And what is theta of the image? From the diagram, what is theta of the image? See, the lens and the eye are very close to each other. So the angle created at the eye is equal to angle created at the lens. That is our assumption, though it is not correctly given in the diagram. It is slightly different because the distance is too large. If it is very close, this is same. Okay. Now we can see theta I is approximately equal to h dash by d. So theta I is approximately equal to theta I is equal to h dash by d. Now what is magnifying power? M at d is equal to theta I is h dash by d divided by theta O is given by h by d, and this gives you h dash by h. And we know h dash by h. What is h dash by h? It is the lateral magnification, the vertical magnification m is given by h dash by h. H dash by h. So we are doing what? We are doing magnifying power, angular magnification, which is the ratio of theta I by theta O. We know theta O is h by d from the previous diagram. From this diagram I said all these angles are small and this distance is negligible. So we can say theta is equal to h dash by d. When it is h dash by d, what is md? Md is theta I by theta O. We get relation, d cancel, we get h dash by h. But h dash by h is m. See, this capital M and small m are different. This is angular magnification, this is the vertical magnification which we did in mirror and the lens, h dash by h. And for a lens, this is given by v divided by u. This is given by v by u. But we know this is equal to, what is 1 by u? From the lens equation we know 1 by f equal to 1 by v minus 1 by u. So what is 1 by u? 1 by u is nothing but 1 by v minus 1 by f. So instead of this 1 by u I will substitute 1 by v minus 1 by f. This is lens equation. Whenever we apply lens equation you have to apply Cartesian sign convention. Okay. Further I will write it here. This is nothing but so I am talking about md, which is equal to m, and that is equal to v into 1 by v minus 1 by v minus 1 by f, which is equal to v by v is equal to 1 minus v by f. But this v, what is v? It is the distance from the lens to the final image. What is the distance from the lens? This is the lens. What is the distance to the final image? It is equal to d, and light is coming in this direction, so this must be minus d. So we can say v equal to minus d. Therefore magnifying power at least distance of distinct vision will give you 1 minus v is minus d divided by f, because focal length is positive. So this gives you 1 plus d by f. This is the final equation. So that is what I am having here. Magnifying power, angular magnification of a simple microscope when the final image is at d is given by 1 plus d by f. I told you at d it is the largest size. So what is the largest magnification produced by a simple microscope? Largest magnification is given by 1 plus d by f. Where is the final image? Final image is at d. Where is the object? It is within the focal length. What is the nature of the image? It is erect, it's virtual, it is magnified. Next one, the second mode, the relaxed mode, simple microscope with final image at infinity. When the final, again I will tell you the first relation that you should keep in mind. What was it? When you see directly, the angular size of the object is equal to h divided by d. When we see an object at d, this is the angular size. But now you need to find out the angular size of the image. Look at the diagram. For making final image at infinity, object must be placed at the focal point here. Image will be at infinity. Now you can see easily that, see, object is somewhere here at infinity and the size of the image is also very large. So if you take this angular size, say h dash, by whatever distance you have here, some distance d, image is at infinity, large height, and the distance is also very high. So if you take tan theta in this big triangle, and that is also equal to theta I. So theta I in my diagram, I do not have to consider the large image at infinity. I do not need this. I do not even need this distance to calculate that angle. That angle is equal to this theta I, which is nothing but h by this distance is f. So the magnifying power, angular magnification, when the image is at infinity is given by theta I by theta O, theta of the image by theta of the object, and what is that equal to? H by f divided by h by d, which is equal to d by f. So this is not from the lens equation. So directly I can take the magnitude of d and magnitude of Cartesian sign convention is applied here. So magnification when the final image is at infinity is given by d by f. But magnification when the final image is at d is given by 1 plus d by f. So when question comes, be careful. If you want largest size image, this is the equation. If you want relaxed division, this is the equation. And you can see this is more than this. Magnification at d is more than magnification at infinity. Now in the beginning I told you simple microscope is a convex lens with a short focal length. Why? Because the magnification is inversely proportional to the focal length. So the shorter focal length you get a larger magnification. How to increase magnification of a simple microscope? That is by using lens of short focal length. Okay, but this has a problem. What is the problem? When the focal length decreases, the lens tends to become more and more spherical, because we know focal length is related to radius of curvature. Focal length is given by 1 by f is equal to n minus 1 into 1 by r minus r1 minus 1 by r2. So we understand that focal length and radius of curvature are related. So when the focal length becomes smaller, radius also becomes smaller. F decreases, then the radius of curvature also decreases. Radius of curvature decreases means the lens will become more and more spherical. It will become like this, spherical. This has got a short focal length and this has got a long focal length. Okay. So when you want high magnification, you go for a shorter focal length. So radius of curvature decreases, the lens become more and more spherical, and this will create lot of like aberration in this one. We call it a spherical aberration. It is due to the spherical shape of the lens, spherical aberration. Spherical aberration will increase. My point is simple. Magnification is inversely proportional to focal length. So if you want to increase magnification, focal length should decrease. This will create spherical aberration, more and more spherical aberration. That's why simple microscope is useful only up to a magnification of 9 times or less than that. More than 9, this is difficult. Theoretically you can have anything, but practically a magnification less than 9 is possible. So if you want more magnification, you have to do something. This is a limitation of simple microscope. So I am ending this topic here with the limitation of microscope. What is the limitation of a single microscope? That its magnification cannot be greater than 9 due to technical problems.